Hello, everyone. Welcome to this first set of streams focused on assembly language, which hopefully we'll be seeing how to use assembly language with robotics. Sorry for the 10-minute delay. I'm struggling really bad with my internet connection. Apparently, there's been a power outage. I think that's the correct word, where I live, and the power is just going on and off. So I'm using mobile data, hoping that it will last long enough for me to give this stream. Hopefully we have the stream as well tomorrow, so we'll do two parts. I would say they're different from each other, so if you attend this one and then you miss the second one, it's okay. Or if you attend the one of tomorrow and miss this one, it's also okay. We're going to be seeing similar things. Of course, it's preferable if you start with the part one, because I'm going to give a lot of back introduction of how everything works on the backside, and not just typing assembly instructions on our editor. So for today, I want us to focus more on the theoretical part of how assembly language works and some of the basics on computer architecture. We're going to learn about some of the commands that you can use to write assembly code. And tomorrow, we'll be focusing mostly on creating a project in Assembly Editor. Today, I'm going to show you a couple examples of how this looks like, and then tomorrow we're going to do a project together. I don't want to overwhelm you with many things, so we'll just start step by step without a lot of things that we have to see today, because there's plenty of things that we need to learn in order to reach that final goal where we're going to write our first code in assembly language. Don't forget to check in. I already sent out in there the link on the chat. Make sure to claim your points and check in into this stream as well. I'm going to leave in there the link on the chat in case you want to check in as well for people that are coming in just now. Great. So for today, again, we'll be doing coding in assembly. This is the part one. So we're just starting. My name is Jocelyn. I'm a coach here at Major League Hacking, and well, I study robotics, so that's why I want to start making streams that are now more focused in robotics. If you have been to my previous streams, you might have realized that I always make streams focused on using new APIs or LLM fine tuning, using vector databases, creating recommendation systems. So all of my streams were focused on AI related stuff and understanding some basic concepts. And now I'll be creating more streams focused on robotics. Why? Because I have seen that many people are interested into these topics, and sometimes they are a bit hard to get into because they're not as simple as, I don't know, reading a documentation page and using an API. So the topics that I'm going to show you today, I tried to make a compilation of most of them that I saw on a previous college class that I had the past semester. I have to admit it was hard. Um, there were a lot of challenges involved in that college subject, but well, I'm going to try to explain it to you in simple terms. We're not going to get a lot into the depth of how everything works because that might take us more than just one stream. But yeah, hopefully you will get some insights of how it all works. Some of my fun facts is that I like Minecraft Bee plushies, and also I love salsa dancing, which is pretty cool. um and yeah, I'm also into neurotech, which is another important topic that I might show up into next global hack, which will be interesting actually. So this is the schedule for today. We're going to be learning about the importance of assembly in robotics projects specifically, and then we're also going to be seeing computer architecture 101. So I'm pretty sure most of you who are into technology and are studying tech-related field, you should have seen a computer architecture with von Neumann architecture. So you have your RAM, you have your ALU, you have your registers. So you have all of your data flow of how a computer actually works. But at some point in college or whatever courses you were taking, we only see the diagram and we learn what each component is, but we don't know how does that even relate on how my computer is working, or how does that weird diagram flow actually process data. So we're going to be seeing that diagram a bit more in depth today. I don't expect you to understand it to 100% because honestly, sometimes I don't even know how to do that. But hopefully, you will get some insights of how it all works. Then we're going to do a brief intro on binary and data representation. So, if you know how to convert decimal numbers into binary numbers, that's good. But what I'm going to show you here today is how these binary numbers actually work in order to produce instructions to our computer. So, we all know that computers only understand zeros and ones. So, that's what they have taught us all along since we were, I don't know, in high school or since we started learning about tech. But we don't actually know how those zeros and ones actually mean something. So to make it brief, the the order in which the bits are organized is how they represent a specific instruction. And those instructions, guess what? Those instructions are the ones that are written in assembly language. So we're going to be writing our first code in assembly, which will be just a couple lines. I don't know, like 4 lines, 5 lines, just to add two numbers. It will be super simple, I promise. And hopefully you will see how all of how the register works and how the data is stored in your computer as well. My goal here is that after this session, you will understand how low level systems work, and hopefully, you will be left with questions and blockers on how this works, because that will make you a bit more well, will motivate you into investigating and learning more by yourself, because honestly, these topics, it's impossible to learn them in 2 hours, 4 hours. They take weeks of dedication into understanding how everything works. So yeah, it's I'll try to explain it as good as possible. Remember that if you have any questions or comments, you can drop them on the chat so I can see them as well. So the first thing, assembly in robotics. So there's many microcontrollers and embedded systems out there that are used for robotics. So you should probably have heard about Arduino, which is the most basic one. But then there's another where there are different families depending on the architecture of the chip that we are using. So we have different architectures for different chips that follow different regulations. And in robotics, we use these microcontrollers because we want to be more precise on the timing and also on the memory management. So if we use regular language, well, a high level language like, I don't know, Python or C++, we might get up until some point our own memory management and we can make it work and our robot will start moving. But then there's certain problems that arise when you are trying to make everything a bit more coordinated and you want the timing to be important. Because the whole point of using low level code is that you want to have full control of your software and your hardware design. So the first important points that I placed in here is that assembly in robotics is used for direct hardware control. So if you want to be in direct communication with your hardware, either if there are sensors, motors, LED lights, actuators, whatever components that you have in your microcontroller, you will be able to control them directly using assembly language. You also want to use it if you want to max performance in time critical loops. So if you want to be super exact on timing, you want to use assembly because that's the only way that you will be able to make your whole calendarization structure into your microcontroller. So the things that we will be seeing today, I'm pretty sure you will end up with some questions about, okay, yeah, we're seeing how to add numbers and how to use assembly language, but where is the timing that you mentioned that is super critical in robotics? So that will be a topic for another stream, sadly, because that's a whole other area of investigation on doing timing and calendarization in microcontrollers. If you want to research more, it's a thing called free artos. I'm going to type it on the chat if you want to learn a bit more on how timing works on microcontrollers. That's another interesting topic that we won't be covering today, because it's a different aspect. And then the other part is for memory efficiency for small microcontrollers. So on your Python language or any other high level language that you can think of, the memory management is not very good. I mean, you create, I don't know, you create a variable and you know that that integer variable will have, I don't remember the exact amount of bits that an integer has, but it will have X number of bits and perhaps you won't use them all. So if you only use, I don't know, 8 bits of the 12 bits that you were supposed to use, then you're wasting your memory in that variable that is just consuming more space on your microcontroller. So that's why in assembly you have to specify exactly which memory address you're going to use and the exact amount that you're going to use. So everything is super precise and stored in super exact memory addresses that you want to have control of. Of course, that also brings you with more complications on knowing how memory addresses work in these microcontrollers. And yep, assembly is mostly used on firmware or bootloaders or things that are more where memory and timing is more important. So if you're building just a car that will move and I don't know, it has a camera and stuff, just your regular a four-wheeled robot, it might be a pain to use assembly. I wouldn't recommend it to overcomplicate yourself. But if you're doing a more complex implementation, then you might want to use assembly in there. And of course, building simple projects with assembly, it's also a great way of practicing how this works and understanding hardware at a more deep manner. And this image in here is of an STM32 microcontroller, which is the, I don't remember the exact model because there's different STM32s in industry, but this is the one that I mostly use for all of my projects as well. Okay, here's just a comparison table of some of the things that I was mentioning already. So another important thing to talk about is how easy it is to erase your code on on a microcontroller. So if you're using a high level code, it will be easy to erase the data that you input into your microcontroller. But if you are using a low level code and you want to erase that data from your microcontroller, it will be harder to delete. So why is this? So for example, there's other microcontrollers out there such as FPGA, and those microcontrollers, when you input data into their registers, so into their nets of where data is stored, so basically in their internal memory, physically those gates are moving in real time. So if you input data for once and you want to delete it, it will be hard to delete. You need to use UV light. Put some UV light in your microcontroller so you can actually delete the data that was stored in some specific microcontrollers. Hopefully, this complication is already in awareness by various engineers, and they have worked into making the erasing process of microcontrollers, of low level microcontrollers, easier to do. So I would say this is more of a learning curve, if you would like to call it that way. What was the name of the microcontroller? STM32. Yep, that's correct. And not sure an FPGA is a microcontroller. Yep, you are totally correct. That's a programmable gate array logic, which is what I was mentioning, that it's hard to delete those arrays that already have data in there. I actually used that one to create a small video game back then, and it was super hard to use because it's in another language. It's not assembly, it's BHDL. So that's a different language that you're using, which in my opinion it's easier. Because it's more related to, I think it's similar to C, uh, but it's different to configure as well. Yeah, but that's another topic as well. Okay, and then the important question on when to use assembly language. So again, time critical code. If you want your code to be in a sync or in a loop, so follow a timing process, you want to use assembly as well. Or if you want to directly control hardware manipulation, that's also another important area where you want to use it. And if you have extreme memory constraints, so sometimes memory is not a privilege that you can have. So I know that most programmers are used on just creating their programs. Like, I don't know, I'm going to build an app that translates Chinese to Spanish, whatever. And they focus more on the functionality of their project because memory management is not an issue. So they can have as much memory as they wish. But when you're working with microcontrollers and I don't know, like a board that might only have like 32 millibytes of storage, then that's when you want to focus on memory constraints. Oh, we have a question here. Hey, sorry I missed the start. How long this recording going on? So it's about 23 minutes exactly. But you didn't miss much. We're just going into the introduction, so hopefully tune in to learn about assembly language. And then there's a whole other debate on when do I want to use C++ or C, and when do I want to use assembly? So if your logic is really hard, so your coding logic is hard, don't go with assembly. Even if it's better for timing and memory constraints, don't go with assembly. So if you want to do something more complex, you might as well end up using C or C++. If you're using a simple automation, something that it's easy to do and the logic is not very complex, then you want to use assembly language. So assembly can be faster than most languages because I can code in C. Yeah, that's also correct. Assembly is faster than high level languages because that's just because it's connected directly to your computer. And in comparison to a high level language like C, is that in C you need to compile it and then you need to do use a translator in order for your machine to understand what the C code is actually saying. And there's also there's C language, but then there's also C bare metal language. So C bare metal language is a more low level representation of C, and I can show you an example um in a while of different programs and projects that I built using C bare metal language, which is hopefully easier to understand than assembly itself. Okay, here's just a representation of how this works. So we have our machine language, which is our binary language, so only zeros and one. Then we have the assembly language, which is instructions. So in this case, mob is instruction, and then we have two values that we want to manage. um, Always the first word in assembly language is going to be instruction. So add, load, store, subtract, multiply. So your first word will always be your instruction in there. And then we have high level languages such as C++, Java, or Python, where you can understand completely in a more human language of what you're saying. So you have your functions, you can print into the screen, you can create variables, you can do loops, and everything is just so simple because it's really simple to use a high level language. Because then when you're trying to create a loop in assembly language, oh, you don't want to do that. That's super hard to do, and you have to think of a lot of things. I remember on my last semester, there was this exam where we had to program a counter in a button and then show it in an hexadecimal display of a microcontroller. And we had to code all that in assembly language. And it was in an exam question. So you had to actually manually write the assembly instructions in order to make that work. I'm actually going to try to look up for that exam to see if I still have those written answers in there. It will be fun to watch. Great. So hopefully by now you understand some of the benefits about using assembly language in comparison to other high level languages. Again, these type of languages are used mostly in robotics because that's where we care more about timing and memory constraints. So you will be hearing these a lot in the robotics field. And now, talking a bit more of computer architecture. So, I'm pretty sure most of you might be familiar about some of the components that are inside our computer architecture, because you might have seen it for a CS class or computer engineering class where you have to learn about how these diagrams actually work. So, I remember learning about this when I was probably in high school, is when I first learned about this diagram. But even after seeing so many YouTube videos and trying to understand how everything worked, I still had many questions on how everything was connected. And then in college, when I started learning about bit management and how those information translates itself into this diagram, it all made so much more sense. So the most important things that you want to see from this diagram and computer architecture is the CPU, which is the core of basically everything. So in here, it's just the largest chunk in here. So the CPU has a lot of things inside it. And then we also want to we care about the memory, which is in here on our left side. And then we also have our input and output ports. Why? Because we want to connect to the exterior. So if you want to connect a motor, if you want to connect a LED light, or whatever thing that you want to connect to interact with your CPU, you want to connect that into the input and output ports, which are also shown in here on your right side. So for the CPU, I'm not going to go super in depth on how each unit works, but just keep in mind that the ALU, in here it's ALU, it's also called ALU, which is the arithmetic logic unit. In there is where all of the operations take place. So if you want to add something, if you want to subtract something, you're going to do that on the ALU. And then the other things in here are just to connect with your memory and with your input and output ports. So if you want to understand something from a CPU, which is core, I would say start with the ALU and then understand how the ALU works completely and how it communicates with all of the external parts that you have in here. Because there's also the program counter, it's also the control unit. So there's many things in here that you want to understand. Hopefully I will show it on a diagram on the next slide to see if we can try to understand how it all works. But yep, any questions so far on computer architecture or probably even insights about the things that you have learned so far? So, question for the chat: is anyone familiar with some of these concepts? Can you tell me something about these concepts that I can read out loud on the stream to see how are hackers doing? I'm going to give a couple seconds for you to type your answers in there. Okay, we have someone that is familiar. Hey, can you tell us something? Probably how you understand on how this work. An electrical engineering student, right? EE is electrical engineering. Yeah, so electrical students, well, electronics students are also super pro into understanding these concepts. So yeah, I'm really sure that you know how all of this works. I know a CPU is a part of a computer and it stands for Central Processing Unit. Yep, that's correct, and we are seeing it in here with the different concepts that are inside of it. FPGA is a lower level than assembly, depending on how you're interacting with it. Because in my case, I was using BHDL, which is the other which is the Verilog language, to control my FPGA. So turn on LED lights, control the switches, control the hexadecimal output. But then I also used GOMNOT, which is a similar architecture for assembly, but it's not quite assembly. And that was the harder part. So yeah, you can also use FPGA with sort of a low level system way to control all of your logic gates, but I would say they're just different depending on the processor that you want to use. ALU arithmetic logic unit, the part that performs the math calculations. Exactly. Yep. So another important thing to know, and thanks Moses for reminding me that, is that the the ALU or the arithmetic logical unit, which I already explained on the chat, and I also mentioned it previously, which makes the whole math operations, is that it cannot perform complex mathematical operations. So you cannot do multiplication, you cannot do division, you can only do simple math operations. FPGA and assembly are different things. Yeah, that I completely agree with that. I know a bit about register allocation and the memory hierarchy. Oh, that's super good to know because we're also going to see about register allocations. I was trying actually before the stream, trying to look um, for a good simulator online to see how registers are being filled. I remember I used one on my course, but I can't seem to find it. So I found one that is similar, but if you will have recommendations um of seeing registers live and how they are being allocated in real time once you compile your assembly language, send over the links on the chat so I can look them up and hopefully we can use them on the next stream as well. All of the parts communicate via buses, data address control. That's totally correct. Yep. Also all of the data it's being sent over there, and yeah, you're right. There's different types of buses. It's very nice that you know that. I guess that is part of operating systems course. Depending on your college, I would definitely need to look back the first 20 minutes. It sounds exciting from the outside to have such an assignment in assembly. Yeah, I mean that was just a class that I took where we had to build these. It was a small car, and the car had to measure the motor's rotations, so get the RPMs, and then it also had to interact with different switches, so different input and output ports, and we use an STM32 and an ESP 32 to control all of that, and all of the code was written. One part was in assembly, but it was just like turning on and off a LED light, and then the other part was written in C, bare metal code, which is not your regular C. I promise you, it's much more complex than your regular C language. Hopefully, I will show that project live so you can see the differences in between. Okay, so thank you for all of your insights. It looks like we have a lot of experienced hackers in the room, so I'm very glad to hear that. Okay, we have a question here. ANSI C. I don't know. What does that mean? Would you be able to clarify a bit? So is assembly connect directly with the CPU memory or the RAM? So that's the code that goes into your whole architecture. We're going to see this in a while, but to get you out of your question, the assembly instructions are all written in zeros and ones. So you have your assembly instruction, and that translates into zeros and ones, and those zeros and ones are the ones that are interpreted inside your into your CPU, if you would like to say it that way. Also, Jocelyn, would you have any recommendation on how to get more into assembly courses, books, blogs? Not talking about go to visit your class instead of sleeping. Yeah, for sure. I can see. I'll see if I can download some of my slides presentations of that course that I took. Because honestly, I recall trying to learn online, trying to find somewhere where I could learn about these topics because I was just so confused from my classes and I couldn't find anything helpful. So that was really stressing because it's hard to learn about these types of things. Um, I would say that when I was trying to study for my exams, I used ChatGPT a lot to explain me things that I wouldn't understand. But I will be happy to share you the slides presentations. Just send me a DM so I can remember and I don't forget after the stream, if you would like. So ANSI C, a version of C used on STM32 Cube IDE. Oh, okay. I see. Then I guess it's that one. Yeah, because I used the online simulator, which was Wowkey, just to see that everything was working correctly. And then when I wanted to upload it to my board, I used the Cube IDE. So it's probably that. It's probably that one as well. Okay, so now for this one, this is a more specific diagram of how everything works. So in here we have three important things. So we have our registers, which someone already mentioned. Then we also have our control unit, and we have our arithmetic logic unit, which I mentioned you was very important. So although it's very important. So here's just how the workflow actually works. So the important thing, registers is a temporary storage. So registered, you can imagine them as small boxes. So you have an array of small boxes where you are storing um, different values. So registers is just to store different values in boxes or arrays. And then you have your control unit, which is the timing. So you want to have timed operations and also enable those operations in there. And finally, we have our arithmetical logical unit, which is the one that performs the task that we are being asked from the specific instruction. So if you're seeing it in here, the ALU is the one that actually performs the task that we want to do, and all of the other sections in there are just to communicate and are just there as a help in order for the ALU to perform the instruction that we want to use. And by instructions, by the way, I mean literal subtractions and additions in assembly. So an instruction, and we'll see these further along, is just a line of code. In your instruction, you have your instruction, you have the address where you want to store that, and also the value that you want to store. So you can see it as variables in some sort of way, but they're a bit different. They're called instructions in assembly language. I am watching you from YouTube, not by Twitch. Can't DM but still interested in any sources from being over it. Oh, no worries. If you are in the Discord channel, you can find me in there. I posted an announcement. Just send me a reminder in there. Can you say something about width sizes and overflows? Oh, that's that's a whole other topic in here. I actually wanted to include a bit of underflows and overflows because there's also underflows in memory. But sadly, I thought it was kind of boring to explain that to you of how overflows work and the different flags that are associated when you have an overflow or you have a negative number, because oh boy, having negative numbers in binary is just a pain. So yeah, I won't be discussing that today, but I'll seriously consider to create more streams where I talk about these types of topics as well. Ollie usually fits into data out of four memory addresses as well as PC. Yeah, to calculate branches. I love your explanation. Yep, program counter is for the branches. I'm kind of guessing that you are already familiar with these types of languages, so happy to hear that as well. Whoa, underflow. Never heard of that. Yeah, it's also in there. So the most popular one is overflow because Stack Overflow, and overflow is just in everywhere where you basically um where you go past the amount that you wanted to store. So if you have a storage of 8 bits and you have 12 bits, then that's an overflow. And your computer can actually manage that. But again, that's a whole other discussion of how bits work and the different flags that are associated with those bits. Luckily, everything is related. So all of the things that you were mentioning on the chat and all of the questions that I'm answering right now on live, they are all related to computer architecture. So that diagram that you saw on your class or when you were in high school or whenever you learn about computer architecture, that diagram is the key to everything. I would say that's like where everything is represented, and it just gets deeper on the way that you want to see it as well. Right, so moving to the next one. So this one, I'm not going to go into a lot of detail of how this works, but this is just basically a block diagram of an arithmetic unit for floating point addition. So if you want to add two floating points, this is how your computer actually does it. So in there are some of the steps, and I actually took this screenshot from one of my courses slides. So yeah, the first one is there are like 5 different steps, and there are arrows to direct it. So hopefully I'll be sharing the slides as well, and you'll be able to see them. Okay, so we have the 5 steps in here. Yeah, I would admit that I took quite some notes to understand how this works. But yeah, just the whole point of using this slide is here is just for you to know that it's very hard to add two numbers and how it actually works and all of the different components that are associated into learning this. Okay, which assembly language are you going to use today? So I was trying to look for different how do you call them, compilers online that will show me how the registers are being filled. I found one that is using leg v8. But yeah, I'll just explain the simple instructions, and then hopefully for tomorrow I'll find a good web page where we can actually represent our code, and I'll be telling you which version which type of architecture we're going to be following. For today, we're just going to understand simple instructions, so no worries about which version we're going to be using today. Okay, and again, another important thing to understand, because we're going to be seeing different concepts, are instruction cycles. So again, timing is super important in robotics and in these types of architectures. So your instruction cycle is composed of 3 different sections. So you have your fetching, you have your decoding, and execution. So if you have if you are familiar with PWM signals, which are basically the signals that you send to your whatever thing you're using. If you're using a motor, if you send a signal, it will be moving like this. So it's a clocked signal, and you have zeros, which are how do you call this, the non-rising edges, and then you have the rising edges, which are where the ones are in there. So everything is timed, and this is actually a signal. So the square is a squared signal because it only has highs and lows. So you have your falling edge and you have your rising edge. And how this works is that you first are going to fetch. So you're going to get the instruction from memory. So you have your memory in your system. You have your box of memory and you want to fetch the instruction from there. So once you fetch the instruction, you want to decode it. So you want to figure out what that means. And the decoding is actually super important because there's a whole different instructions that you have to follow in order to decode what the instruction means. Hopefully, for today, we're not going to be seeing how the decoding actually works. So we're just going to assume that we know what the instruction says. But yeah, that's the second step. And then the third step is executing. So performing the actual action. So depending on the action that you are going to be dealing with, if it's just adding two numbers or moving a motor or turning on a LED light, that's the execution. So when the action actually happens. We have another question. Are you going into pipelining today? Pipelining. Um, I don't think so. I'm trying to remember how does it relates, because I do remember something, but no, we're not going to be seeing that today. I didn't even think about it. Okay, so instruction cycles, again, there's three sections: fetching, decoding, and executing, and everything is timing. Everything is time. So you have your clock cycle in there. And your clock cycle, again, it has falling edges and rising edges. Okay, and then our, I would say, one of the most important parts to understand um, from this presentation are registers. So registers, what to say about them? I don't even know where to start. So your registers are just you can imagine them as different cells that you have in your memory, and they're small. So you have your registers, which are different cells, and each one of them they have a different naming. So they can be called either A1, A2, A3. There's also R1, R2, R3, or X1, X2, X3. So it depends on the architecture that you are based in, but they are basically different spaces of memory that you have. And there's different types of registers to deal from. So you have your data registers, which is where the number or the actual value that you want is stored. And then you also have your address registers. So address registers is the direction, and the direction is usually given in hexadecimal format. So if you're familiar with X codes, hexadecimal representations with the 0x and then the combination of numbers and letters, so that's how the information is actually stored. Yep, and then we can interact with them. So the whole way of interacting with them is um, through your instructions that you're going to be writing into there. Addresses. Yep. Why? Because on your you can see it as a square. So you have your square and you have different cells, and each cell has a different value. But how do you know which value to access? You need to know the address to that value. So in order to retrieve that value in your code, you need to know the address of that location. Um, so if you're familiar with C pointers or C++ pointers, you know that a pointer is it's pointing to a space in memory, right? So that's how it actually works on the backside. So you have your data, and the only way of knowing where your data is stored is to link it with a specific address. And address is just a representation in hexadecimal format. There's also different types of registers. So again, there's the data registers and address registers. You also have this can go from 0 to 7, so there's different numbers of registers in here as well. Okay, I'm going to do a short 3 minute break because I'm just going to go grab some water. But I'm going to leave this slide over here so you can fill it in and then leave your questions on the chat when I come back so I can answer them all on this slide because I would say this one is super important to understand as well. Hello, hello. I'm back. I'm just going to move that banner. Okay, so we have some questions in here. Are there only three types of buses? Um, from my experience, I want to say yes, because that's the only ones that I've heard about, but I'm not sure if someone with more experience knows the answer to that. I want to tell you yes, because that's honestly the ones that I've seen like forever, but it might be different, so I'm not 100% on this answer. What function does a control bus serve? Oh, so this is actually a nice question. So you might be assuming some things from this diagram. So address bus, again, it's for addresses. You have your data bus, which is for the data that you want to transport. And the control bus is actually one of the most important ones because it actually tells you what you're going to do. So just by the word of what it's saying, it controls how your logic is going into your whole diagram. So you're not only seeing these types of buses in here, so you're also going to see these ones like for example in here you're also using different buses. In here there's also different types of buses. If you see in here these lines, this is one bus in here, then you have another address bus in here. So there's different buses in whatever computer architecture you're seeing. Okay, and moving on now from the registers. So hopefully this was clear for all of you. So for registers, you can see it at different cells where you store data, and each data has an address that is linked to that data that you just recently stored. Why? Because you want to know where you stored that data. Again, you can relate this to pointers in C languages as well. Okay, and here's also another nice representation of this. So we have our memory in here, and you have the different locations from your memory. And then you also have your address for reading and writing data. And you have your data to memory and memory to data over here. So everything is connected into the memory. So again, as we were seeing on the previous diagrams, you have your CPU, and your CPU connects to the external memory, or the memory that you have for your whatever architecture you're building. And then to connect in between those you want to send the data, and also you want to send the address that you are going to be reading from. Why? Because there's different instructions, and I'm pretty sure you know these instructions from being software developers. So you have your read instruction and you have your write instruction. So if you're just going to read, that just means that you're not going to modify any register. And if you're going to write, that means that you're going to be writing a data input and also your address. So it works different. You can read multiple addresses at the same time, but you cannot write them at the same time if you would like to see them that way. And in here on the memory, you have the different, you have the tower of the different memory allocations. Again, you can see it as different cells that contain different values as well. Okay, and then we have memory organization. So this is the one where most people are familiar with the different types of memories that are on your computer. So the ones that we always hear is the RAM and ROM. So RAM, random access memory, and then ROM, read-only memory. So difference between them. So RAM, it's temporary data that you want to store, and then your ROM or flash is your program and storage. So for example, if you are building a robot that has different sensors and you are using a microcontroller, the code will be stored in your flash memory. So all of the instruction and relation about how the programs work, it will be stored on your flash memory. And then over here, there's different insights on each one. I like this image because I thought it was cute from the different representations of the ROM and the RAM as well. So RAM is the memory that's available for the operating system programs and processes that your computer is currently running. So that's why when you are buying a new computer and you have a computer that has 8 gigabytes of RAM and you have another one that has 32 gigabytes of RAM, you're going to go for the one that has 32 because you have more memory available for your programs to run. In other words, your computer will be faster. So that's why people that are into tech, they always want to have more RAM memory. And you can look it up on your computer as well. If you open up your computer, or if you have ever opened it up a computer, you'll see that this a small card about this size of large. They're usually green. Um, you usually have two slots on your computer, well, in your motherboard. You have two slots, and you can usually upgrade to more um, RAM storage on every computer. So for example, if your computer has a built-in 8 gigabytes of RAM memory, you can you can most probably update those up to 32 if you buy more RAM, of course. So if you buy another chunk of that memory, and you open your computer and you connect it in there. And then the second one, which is the ROM, it's a memory that comes so pre-built with your computer, and it's the one that works for storing all of the instructions. So all of your program information, all of the instructions that you want to do for your for booting up your computer or your hardware or whatever piece of thing you're using, you're going to store that on your ROM memory. So two important difference. The RAM, it's a volatile memory. So what does this means? That if you shut down your computer and then turning back on, your RAM memory will be wiped. And from the difference of the ROM memory, your ROM memory is non-volatile memory. So what does this means is that it will stay on your computer for like forever, unless you manually delete that. Which I'm pretty sure you don't want to delete your ROM memory on your computer, because then you will have failure issues on boot loading your computer again. Okay, and then we have some definitions in here: random access memory and read only memory. Yep, exactly. RAM and ROM. I actually have a question for you. Um, if you know a bit more of this than I do, what does RAM is called random access? I mean, does it has to do something on like the access to it is random? Honestly, this is a question for the chat that I would love to hear from you. If you can Google it or just mention it to me during stream, it will be nice to know, because I think that's a question that I have always had, and I think that I had looked it up, but I usually forget things. So you can read from any cell. Oh, I thought it was going to be something more interesting, like something cooler, because that's what I was thinking, that you can access um any memory register, but you don't start to read from the entrance. Mm, okay, now this is interesting. Yep, different apps can have cells side by side. Okay. You are very smart. Thanks for letting me know that. And hopefully now the chat also knows, because I'm pretty sure that's a very common question that I would, if I was a teacher, I would ask that on an exam. Like, why is a RAM called random access memory? That would be a very interesting exam question, because any memory location in it can be accessed directly and in any order. Oh, I loved your explanation of it. It's very simple and very direct. You can access any location in the memory directly and in the same time. Okay, that sounds about right. Okay, thank you, hackers, for hopping in and doing some awesome explanations. Honestly, I always like how you describe things. Great. So moving on, there's also, well, so far we have seen three important things, right? So we have seen the instruction cycle, so how instructions are decoded and executed. Then we have seen registers, which we have data registers and address registers, which are stored in a cell, in different cells. Then we have our memory organization. So we learn about the difference between RAM and ROM, which we already know. And finally, we have input and output ports, which I would say are the most I mean, they're not hard to understand, but they are definitely hard to configure. So this is a screenshot that I took from one of the architectures of the STM32, which hopefully, if you have very good eyesight, you might be seeing that there's different numbers with letters in there. So PA, P12, P13, P4, P2, and so on. So there's different ports in there that you can connect to your STM32. So the way that you are going to access to external things, or if you want to read things from external sensors or motors or whatever actuator you're going to use, you're going to access them through input and output ports. So if you have ever used an Arduino before, you might have realized that you need to input things on your Arduino. So you connect your cable into your Arduino port, and then you connect that cable into your LED light, and then you tell the Arduino code um, that you're connecting your LED into, I don't know, port. Um, I think there's A1, like the analog inputs, or the number 12. I think there's the pins in Arduino are with numbers, if I don't remember incorrectly. So you go into your code, you declare your pin, and you mention that you are going to be connecting your LED light into pin 12 or 7 or whatever pin you're connecting it to. So that's what input and output ports are. But now, what happens when you are trying to configure those ports in a more complex chip in the low level format? So libraries and components like Arduino, you just manually select the pin that you want to use. So you just say, okay, I'm going to use pin 7, and that's it. But when you're going into STM32 and how to configure those pins from the backside, there's some bit manipulation that you need to do in order to configure your pin correctly. Why? Because you need to actually tell your computer that you want to configure that pin as an output, that you want to configure that pin as, I don't know, pull up, push up, or that you want to configure your pin as whatever configuration you want to have. So all of the configurations that you want to associate to a specific pin, you want to tell that using GPIO registers. I'm going to show you in a while when I show my code example. I'm going to show you how this actually works. So how can you actually configure a pin? But it's not just by saying pin A equals port 7. It doesn't work like that. So in real life, I know you have worked with these types of microcontrollers before, where you just connect your pin and say that it's going to be connected to 7, and that's it. But how it actually works is you have to configure the bits and how you're going to access that port manually. So all of the configuration is done manually. So there's different instructions that you need to follow in order to make your pin work. And if you did not do that configuration properly, so if you missed the address, or the address that you selected is incorrect or doesn't exist, then your input and output port will just not work. So here's an example where you can connect your GPIO register that controls to an LED light. So that's just a simple example of how it works. All right. So now going into our last topic, well, almost last one, which is binary representation. So I know we've seen so many things before that are related to computer architecture, seeing registers, seeing how the bits are the basic element for everything in computers, basically. So now we're going to learn about how these numbers are actually represented in binary format, and how can you communicate using a binary representation. But before going in that, we have a question in here. What would you advise for a beginner to deal with STM, ESP, Arduino to give it a try with? Like, say you purchase a board or a kit. I mean, one has to start somewhere, not necessarily about the platform. So if you have never used hardware or built something using electronics and coding it up, I would strongly recommend you starting with Arduino. So once you master Arduino and you know how to connect everything, and you know how to code basically anything. So if someone comes and say you program this sensor, and you can do that, then you can move on to something more complex like STM32. Zeros and ones. Yes, exactly. Trying turning bulbs on. Yeah, for sure. I would say the simplest project that you can build is turning on an LED light using your Arduino. And also, Arduinos are fairly cheap, so I wouldn't recommend buying the original brand, because then that one is expensive. But you can get a Chinese board for like around, I don't know, less than $5, less than $5 USD, like yeah, $5 USD is a standard. They're very cheap as well. Or sending some message to turn an LCD. Yeah, for sure. There's a lot of projects that you can start with from using your Arduino controller. All right, so now for binary representation. So why does binary representation actually matters? Because it's the key of everything. So if they ever ask you what's the basic unit for computers and how to understand computers, it's binary. So zeros and ones, um, which are um, which are also called bits. So a zero is a bit, then one is another bit, and then zero is another bit, and so on. So bit is the basic unit, is a basic unit of memory. Any 8 bits is equal to 1 byte, which byte is the more standard notation that we use when talking about storage. So you can talk about 32 gigabytes of storage, or megabytes or terabytes. We're not going to say like 142,000 bits, because then that's a whole lot of things. But yeah, binary, on is equal to 1, off is equal to 0. That's a basic representation that anyone can understand. And why does it matter? Because all the code and data is reduced to bits. So anything, any instruction that you're going to tell your computer, whatever thing you're going to tell it, it's going to be a representation in binary system. I'm not going to explain how to convert from decimal to binary, because honestly, um, I don't care about that. So it's nice if you know how to do it. It's nice if your school is asking you to learn how to do this. But for real, you're never going to be in a scenario where you need to actually convert a binary to a decimal when dealing with robotics stuff. So yeah, it's nice if you know how to do it, because you seem like super smart. It's a nice skill to have, honestly. But you will never be in a scenario where you need to translate a long number into decimal just because you want to know. I mean, I have never been into that scenario. I just look for binary calculator online and then just translate it in there, because that's the easy way to do it. But yeah, just keep in mind that the binary numbers can actually represent themselves into different numerical systems. So you have the hexadecimal numerical system, and you also have the decimal numerical system, which is the one that we commonly use from 0 to 9, and then you have 10, 11, and so on. So here are the different number systems that I was mentioning. So you start off with the machine code, which is binary. Then that machine code, you convert it into hexadecimal. And then finally, there's the assembly as well. So you start all the way down: assembly, machine, binary. As I was mentioning, your assembly code will be each new line in assembly will be a different instruction. And each instruction is then translated into binary language. So you can actually code assembly in binary. So you can create a code just with zeros and ones. But we're not going to do that today. We're going to learn about how to use instructions, um, which the compiler will actually know which translation it is. And I think I forgot to include an important picture in here. Let me see if I can find this one. Instruction opcodes binary. Let me see. Okay, I'm going to share my screen so you can all see it as well. Da, da, da. Instruction opcodes. There it is. So as I was mentioning, your binary will translate. Well, your instruction will translate to binary. And I was mentioning you that you can actually do zeros and ones to do your assembly language for your computer to understand you. But that's not how it works. So how it works is that you have this. I mean, I don't want to explain you all this. I want to find a cool representation. Probably this one. Okay, this one's quite fair good. So how it works is that you will have your instruction, right? So if your instruction is either addition, subtraction, loading, storing into memory, you're going to have a representation of that instruction. And way of representing that instruction is using this. So it's a thing called opcode, which it has 6 bits, so it will be 6 bits of zeros, of a combination of zeros and ones. And the combination of zeros and ones is actually the value that you're going to have. Oh, this one's perfect actually. This one's perfect. Yep. So you will have your opcode, which is your combination of zeros and ones, which is basically the instruction that you want to do. And then you have all other different registers that you can configure as well. But yeah, that's just how, for example, in here in this example, they're trying to represent the add instruction. So add B plus C, which is adding register 2, register 3, register 4. So you have your 3 registers and you store it in register 2. And then this representation, it's written in this binary language. So this blue thing over here, it's equal to this number over here. So the combination of zeros and ones. And there's actually a logic on how to convert this into the different values that you have in here. We're not going to go into that today, but just keep in mind that every instruction that you write can be represented like this in binary language. Right? So now going back. Okay, hopefully you were able to see my screen. I don't know if you were able to see it. Okay, we have some comments in here. At what level should one start learning FPGA? I mean, I would say if you have a good understanding of hardware, if you already played long enough with Arduino, built a couple projects, and you feel really confident on how it works, then yeah, you can start learning about FPGA. But they're quite expensive. So buying one of those programmable boards, they're a bit expensive. So try to see if you can borrow one from your university laboratories to see if they have one that you can use. Because in my opinion, I wouldn't buy one for myself just to play around. But yeah, uh, definitely see if someone can borrow you one. At 10, the value held in the address EBX. What's that? Oh, yeah, the instruction that's in here. Exactly. But above 9 to 16 are in letters. 9 to 16. I don't. Is that for the hexadecimal thing? Or what do you mean by above 9 to 16 are in letters? Nope. Okay, Raul, you have your side conversation going on there that I think I'm not getting it completely. Okay, but yeah, now you understand how the instructions actually translate into these set of binary numbers. Today we're going to be focusing on learning how these instructions actually work. So I was telling you that there's also this whole debate. Well, not debate. There's also this whole of learning curve when trying to configure your input and output ports, so your GPIO A's ports. So to configure those you need to learn about bitwise operations. I'm not going to go super in depth on how this all work, but just keep in mind that when you learn about AND, ORs, source, and NOTs, those are really important. Why? Because when you apply these ones on your code, you are performing certain operations into your bits. So here are some examples of how this operator works: left shift, right shift, bitwise and so on. So these operators, you'll be seeing them a lot when you are working with C bare metal. So if you want to configure a pin, you'll be seeing this a lot on your when you're learning from this. I'm not going to go super in depth on how to configure a port, but just keep them in mind that they exist, and this is a way on configuring your pins correctly if you want to do the actual configuration manually instead of just saying that pin number 7 will be connected to port 12 or whatever. So yep, bitwise operations, another important concept in there. All right, so now going into assembly code. And before we actually go into learning different instructions, I'm going to show you a sample project for the so you can familiarize everything. So all of the things that we learned today, so you can apply them into a specific example. So let me just look up in here this project. Give me a moment. My projects, let me see. Right, so let me share my screen now. Mm, there we go. Okay. There it is. So hopefully now you should be seeing my screen. I'll check your questions in a when I stop explaining this because I cannot see both screens at the same time. But yep, here are different examples of projects that I built. So let me see one simple. Mm, okay, this one might be useful. All right, let me zoom this a little bit. Let me see if I can find it. Okay, so over here, this is a simulator online that I would strongly recommend you to use if you want to build projects. So Wauki has Wokwi. I think it's pronounced Wokwi. Weird. Yeah, but this simulator online has different boards that you can use. In my case, I'm using the CM32 Nucleo and then this board model. But there's different boards that you can use. You can use Arduino as well. You can use STM32 and I think Raspberry Pi as well. So you can use any board if you don't want to purchase these boards and you want to code them and connect different things, because you can also add different components in here. So you can add LEDs, resistors, and a whole other components that you can add to interact with. And you can connect everything here and then write your code and create different files in there. So as mentioned in here, this sample code, so this bare metal in C code is just to blink the LED. So the built-in LED in here, that's LD3, LD4. So those two LEDs and LD2 as well are the ones that we're going to try to turn on. So again, as I was mentioning here, all of the program information is stored in your flash memory. So that's why in here we have flash, flash, and flash again. And then to configure your GPIO ports. So remember when I was telling you that it's very hard and challenging to configure an input and output port? So if I were to configure one of these ports, so port number, what's this, PD2 or PA14. So to configure each of those, you need to do all of this thingies over here. So in here, hopefully, I already wrote down the comments in there, but these are the operations that I was telling you about. So this operation in here is to shift the bits, and then this one in here is to create a mask, and this is the AND value. So in here, you're resetting the pin PA5 low to turn off the LED. So if you want to turn the LED light, this is how you do it. And then you want to clear the pull up, pull down bits for PA5. So you want to delete all of the pins that are in there. Then you want to clear the output type. And then you want to set this pin, so PA5, to output. So how do I know that PA5 is this? Because in here I'm mentioning the base address, and I believe the base address is in here. So GPIO A base, and this is the base address. So there's an actual address defined in hexadecimal format. Okay, and this is just to make the LED blink. I'm not going to explain the whole code, but you can have an idea that everything related on configuring different pins and output ports is using this notation. So if I were to explain you how the mask and bitwise operation works, I will need to at least dedicate 1 hour into explaining the different tables, because it's not only understanding this, but you need to understand the a specific architecture for this for the chip that's in here. So we would need to go to the documentation of the board, see how the memory registers are structured, and then see which addresses are the one that correspond to into the pin that I want to configure, to know how many bits I need to move and how many bits I need to clean or clear in order for my pin to work as an output or as an input or whatever configuration I want to give to my specific pin. Okay, this one, just to be clear, this one is not assembly language. This one is C bare metal. But if you know how this works and how the bitwise operation works, then it will be much more easier for you to understand how addresses and data is stored using an assembly like structure. Right. So let me go back. Okay, so going back to our presentation, and we only have one more thing left to cover before we finish here. So, as a wrap up, before going into each of the individual instructions, there's many things to know um, about low level systems and how they work. It's hard. I know that it might be challenging, and some of the things that I showed today might leave you with plenty of questions, and that's completely okay. The first time that I saw these concepts, I was super confused and I had no idea what was going on. But with practice and learning and seeing some YouTube videos, hopefully, and putting this into practice, so building your own projects, you'll be more familiar. Because the best way of learning, I have to admit that it's by doing a project. So if you build a project using these concepts and trying to see how the memory is managed and how the bits and the output pins are configured, then I'm pretty sure you'll get a lot of things insights on how this all works. All right. So now I guess I want to ask the chat some of the projects that you built in robotics so I can learn a bit from you as well. So if you have ever built a robotics project, you can share it on the chat so I can see which types of projects the crowd is building. So hopefully for next streams, I can do something similar or see what we can learn together as well. So I'm going to give a few couple of minutes for you to type in there how you have used which robotics projects have you built. Let's see. I want to see some projects in there. I mean, you were mentioning very advanced questions, so I assume you might have worked with something related to robotics as well. Okay, we have some comments in here. None for me, but I built BF compiler that had me write assembly code. What is BF? I am sorry. I'm currently planning on building something with a ESP32. Oh, that's interesting. So for using ESP32, I would say you can create something related to controlling something with IoT. So that's usually what ESP32s are used for. So I remember when I was little, I always wanted to build something where I could control like my lights and my coffee maker and all of those things. I know that back then it was not very common to have your smart house, like when you control it through your phone, like your lights and all of that. I remember it was very trending, but back then IoT technologies. I just guess now that is just forgotten because it's now common for all of us. Built maze solve in my first year in an electrical engineering course. Oh, that's interesting. Maze solving. So one of those robots that are autonomous and they are tracking to solve the maze. Is that what you mean by that? It's supposed to automatically close my blinds and turn them on. Oh, that's cool. That's definitely cool. That's definitely cool. Yeah, you're definitely building the project that I wanted to build when I had a lot of time back then. Okay, and then we have it uses a stepper motor. Oh, interesting. Yeah, that's definitely connected to ESP32 as well. It's an esoteric language with just characters. Oh, I have heard of that one. I think I saw it on an Instagram reel back then as well. Wow. You're definitely going with hard things. Hey, but it's nice to see that there's a lot of hackers out there that are not only into software but also into hardware hacks. Honestly, I always love to see hardware hacks on hackathon projects. I just get really excited. I don't know why, because I just know that that team that builds something with hardware, they just went through a lot of debugging and trying to make their prototype work as well. All right, thanks for sharing your projects. If you have more, drop them in chat. I'll be reading them as well. Okay, so going now into the different instructions, well, most common instructions, because there are definitely much more instructions to understand. We have this set of things. So we have mob, which is the move or load. It's also known as load as well. The value into a register. Let me see if I can. Um, I wanted to like circle things. I guess I can't do that. To point you, but I'll just read them. No worries. So starting with the add instruction. So again, as I mentioned you, each assembly line is a different instruction. So every time you create a new line or add a new line, you're creating a new instruction. So for example, you are starting with the add. So add is instruction that we're starting with, and it always goes in the beginning. And then you have these three elements that go afterwards. So the R2, R0, R1, and all of the R's that you're seeing are registers. So R is called register. And for this case, you're adding the values in R0 and R1, and you're storing them on R2. So how this works is that you have your add, and then you're adding R0 plus R1, and then you're storing that in R2. So you can see R2 as the variable where you're storing your output. So I don't know, if in R0 you have 5 and if in R1 you have 1, then you'll be adding 5 plus 1, which is equal to 6, and now R2 will be equal to 6 in there. And it's the same for the subtraction. You are storing the subtraction between R1 and R0 and storing it in R2. Then there's also the multiplication in here. And then you also have the load in there. So the load, it works more when you want to load it into memory, but you don't want to store it. So a store is a different instruction in there. So the load is just to load a value, but you don't want to store it like permanently. So you just want it to be hanging around in there for you to access it later. So in this case, you're loading a value in a memory address. So for example, we're loading the value of R0 into this memory address. So if R0 in our case has number 6, which is the result of the addition, then you will be storing that into the into this memory address in here. But yep, I'll give you a second to read on this table and try to see how these ones are actually related. So we're not going to do a complex code today. I just wanted to be familiar with these instructions, try to understand them, try to play around with them. And then on the second stream, we'll be actually building a project, um, a more complex project where I won't be explaining all of the basics. I mean, I will still explain the code, but I won't go into all of the architectural explanation that I gave before in there. What flavor of assembly is this? I don't know. I just wrote it in the simple instructions that are common in most assembly variations, but the one that we'll be using tomorrow will be leg version 8. So I'm going to type it in there. Leg E8. And I can also share the simulator as well. Let me just find it in here. There it is. Yeah, so a bit of context on what this hacker was asking in this. It's because, yes, assembly has different variations, not because they are different languages. The reason because of this is because we have different chip architectures, and every chip works differently, and they have different versions that they use. So there's different variations of the assembly language, but overall they basically work similarly. So you will always need to store things into registers, and you will always need to load things to different memory addresses. So in this table, you can see just overall how it works. Probably in a different variation of assembly, you will find that MOV is named differently, or that LED, the load one, will be named differently. That can happen, but that's just if you compare, I don't know, JavaScript with C sharp. So you have the same variables and you have the same cycle logic, but they have different syntax variations, and that's the same with assembly in here. So don't get scared if you look up for assembly language and you see different variations out there, and different definitions. There are different syntaxes that you can use to represent these instructions, but they will always follow this structure. So you will always have your instruction, and you will always have your registers that you want to store in there as well. Let me see if I can find an image to describe this. Let me see. I want to find a nice image to see how this works so you can get it a bit better. Mm-mm-mm. Oh, also, I'm just remembering another important part where I have used assembly is when I'm doing capture the flag challenges for cybersecurity, and you want to do reverse engineering challenges. You want to decompile your application or whatever software they give you, and you want to decompile that into assembly. So your low level code in order to find how the data is being managed. So that's another way of using assembly language for cybersecurity as well, to find potential threats and how and reverse the whole engineering on the program that you're using. Mhm. Okay, I couldn't find a nice image. The ones that I could find are very confusing, and I honestly don't want to confuse you. So I guess I'll just wrap up with this table. Try to take a picture of this so you can research a bit more for tomorrow, because tomorrow we have the second part. I'll share this slides presentation on the Global Hack Week chat for Beginners Week. I'll share this with you so you can have it as well. And for tomorrow, we'll be focusing completely on the project. So no worries for people that were not here to complete the stream or were not able to see or attend today. We'll be doing the second stream tomorrow where we will be building a project from scratch. So I'm going to find a nice simulator online that we can use. I'll probably be using Wowkey as well, or the one that I sent over on the chat as well. And we're going to be building a project from scratch using assembly language, and we're going to see how the different values are being mitigated into the different registers that we're going to be using. And hopefully if you review today's stream and see today's slide and try to research a bit more, for tomorrow everything will be much more clear when we start working and when we see how it all relates. Okay, so Thank you everyone for attending this stream. I know we saw a lot of technical concepts. I usually try to give half and half, so half theory, half workshop. But for this case, I had to take the whole 2 hours to explain how everything works on the backside. So for tomorrow now, you will be super prepared with all of the concepts. Again, if something was not clear, feel free to ping me on Discord or review this stream again, and I'll also be sharing the slides presentation in the Discord channel as well. Bye, everyone, and I'll see you tomorrow. Remember, if you haven't registered for this event, please, I already shared the link in there on the chat, and we'll be having more streams coming along as well.